So again, we're making a transition from studying exponential functions and sequences, which are proportional changes or linear changes in the output values, to start to look at a different type of function. But the first couple lessons here in this topic, Unit 2, Part 2, are going to be just about functions in general. Today is called composition of functions, where we're going to talk about composite functions. Sometimes in math, we're going to take a value of a function and immediately plug that output back into another function as another input. So when we plug an output back in as an input, that's called a composite function. So it's like one input becomes an output, that output becomes an input, which becomes an output, which becomes an input, which becomes an output. So it's like a waterfall effect of using different numbers. There are two ways that we can write composite functions. You guys can see my color code here, yeah? This is pronounced f of g of x. And if it isn't my biggest pet peeve calling this fog, do not call that fog. It is f of g of x. Say it after me. F of g of x. This is written like this sometimes with the little circle, or it is written as the composition written this way, which is f of g of x. Please say it correctly when we're referring to f of g of x. A function itself can often be decomposed into two less complicated functions. So if we have a complex looking one and we notice that we have a function inside the other function, we can decompose them. And that way one entire function would replace the variable in each instance of the function with that particular that it was composed with. So I'm going to stop reading for a second. We're going to look down at example 1. Example 1 says to rewrite the given functions as a composition of two functions, f of x and g of x. So what I want us to do is look at these functions and notice that there is a function inside of a different function. For example, do you see how this x plus 1 is like inside this square root? X plus 1 is a linear function. We have taken that linear function, the blue one, and we've put it inside the pink square root, which means we can decompose this into two functions, the outside function f of x being the square root of x, and the inside function g of x being x plus 1. So I took the x plus 1 and I put it inside the square root. Do y'all see that? In example 2, do you see that there's a function inside another function? What function is on the inside? X plus 1. What function is on the outside? Something squared. And when we don't know what something in it is in math, what do we usually put in that place? A variable, right? Like a placeholder variable. So what we would say is the two functions are the outside function f of x being something squared, and the inside function g of x, g of x, being that same x plus 1. We have decomposed this function that's complex into a linear function and a quadratic function. If you look at letter C, do you see how there is a function plugged into another function? What looks like it's on the inside? Just in general, what looks like maybe could be the inside of this function? The bottom. That looks great. So this denominator right here, what kind of function is that? It's got a squared in it. Quadratic. That quadratic is plugged into this rational function 1 over x. So we can decompose this into two functions where one of the functions, the outside function, is the rational function 1 over x. And the inside function, g of x, is x squared minus 3x plus 1. I have taken the g of x and I've put it inside of the f of x. What do you guys think is the inside function for letter D?
3x minus 7.
Nice. So again, we notice that there is a linear function right here. And what is it inside of? What are these called? Do we remember? The absolute value bars. Nice. So that's an absolute value function. So we would say that our outside function f of x is the absolute value of something. and that something that's on the inside, g of x, is the linear function 3x minus 7. So we're just taking complex functions and again undoing composition, basically taking one function out of it to say the h of x or j of x or k of x or r of x functions were made by putting one of these functions in the other. Here's what a multiple choice question might look like for this kind of question. It says, whoa, hello, why is that moving? Let's see, did it stick now? Okay. Two functions f and g are composed such that f of g of x is equal to 4 times 2 to the x minus 5. Before we keep going, what function is on the inside, f or g? G, yeah, because look how it has g straight up on the inside of f. When we're doing composition, you always make sure you see that because sometimes that order will be reversed. But in this instance, the g is still on the inside. The question keeps going and says, which of the following could be the expressions for f of x and g of x? Okay, so let's look at our actual expression here. What looks like it's plugged inside of something else?
2x minus 5.
Super close. A little bit further. Wouldn't you say that this right here kind of looks like it's plugged into like a 4x minus 5? But that x position, that linear function x, Colby, that's your seat right there, is where we put the 2 to the x power. In which case that means the inside function g of x is going to be this 2 to the x power, and the outside function is 4x minus 5. Because we've taken 2 to the x and plugged it in the other function. If I was checking the answer choices, here's 2 to the x as g waiting to be plugged in here, which would make 4 times 2 to the x minus 5. The correct answer here is A. As a little bonus, because we're still learning, what would it look like if C was the correct answer? If we're going to take the g of x function and plug it into the f of x function, what would that function look like? You're taking the g of x function and you're putting it in the f of x function. Meaning I'm putting that entire 4 times 2 to the x. Say again?
Would the 4 be outside?
Outside of what? Because maybe.
The 4 would go to the 4 is the f.
So remember, in function composition, you're taking an entire function and putting it in another one. So I straight up want to take this entire function and put it in this one. And when I say put it in this one, I mean replace every x with that function. So if I were to do that here, need more space. If I were to plug this in right there, hello, come on. This would end up looking like 4 times 2 to the x minus 5. So here's an interesting point. That also answers this question. Isn't that what we started with? 4 times 2 to the x minus 5. So this question actually has 2 correct answers, which is interesting. Let's see what it would look like if we did B and D. These are both incorrect answers, but let's see what it would look like if we take the g of x and we plug it inside the f of x. So for this, if I take this g of x and I plug it into the x position on f of x, what would that look like? Very good. 2 to the power of 4x minus 5. So that one is not correct because we composed them the wrong direction. And what would it look like if we had answer choice D? We would again take the 4x, plug it in where the x goes. So what would that be? Minus 5. Interesting. So composition is just taking one thing and plugging it into another. Now Now when we're doing this and we're actually doing the composition, we're going to go back up to the top and read one more piece of information from the top. When we are actually composing two functions, which is what we just did when we looked at answer choice B and D, because we composed them, the domain of the function f of g of x has to be restricted to the input values of g, for which the corresponding output value is in the domain of f. This means that we need to find and use the domain of the inside function. That's important. I'm going to double highlight that for me. Of the inside function, as well as the domain of the final or composed function. So if there's a restriction of your domain for the inside function that you put inside, or for the final function when you finish this problem, that has to be included in your domain. Here's what I mean in practice. If we look at example 3. Example 3 says to perform the composition below, then state the domain of the composed function. We're going to find f of g of x given these two functions, f of x and g of x. Everybody highlight it again with me. So what function is on the inside? G. What function is on the outside? F. So here's what we're going to do when we compose our own function. We look at the function when we start and we think about its domain restrictions. What kind of function is f? What kind of function is f?
Wait, what do you mean?
Like, is it linear? Oh, it's quadratic. What's the domain of any quadratic? What kind of numbers are you not allowed to plug into a square root function? Negative, which means that the domain for this function is from 0 to infinity, because we can't plug in a negative number. When we go to do the composition, we have to include the domain of the inside function and then the final function. So if I go in here and start to do f of g of x, I'm going to leave the f of x on the outside, but I'm going to plug the inside function in. You guys told me that g was the inside function, so we're going to take this blue function right here, and we're going to put it on the inside of the f function. Boop, boop, just put it in there. Then f of square root of x means that I'm going to put a square root in the f function everywhere there's an x. So this will look like something squared, and that something is still going to be my square root x. Oh, interesting. I have square root and squared. What happens there? They cancel out. So what am I left with? Just x. What kind of function is just a regular x? Linear. Is there any domain restrictions on linear? No, so my final function has no domain restrictions. However, the domain of the inside function is important. Our inside function was this g of x. And so I have to include that in my domain restriction, which means the domain of this final function is still only from 0 to infinity, even though it's a linear function that has no domain restriction, typically, because the function I plugged into it had a domain restriction. But let's see what happens if we do this composition in a different order. Look at question B and compare it to question A. What's the only difference here? The f is inside now. Ooh, interesting. So this one would be pronounced g of f of x, where g is on the outside and f is on the inside. So when I go look at my two functions to begin with, they're the same functions. So it's a quadratic with no domain restrictions, and it's a square root with the domain restriction from 0 to infinity. And if I go to put the f inside of the g of x functions, here's what it might look like. We would do g of f of x is equal to leave the outside function there and take the inside function, which you guys told me is f of x, and plug it in. So boom. I've plugged in the f of x. Just like the blue kit you did at the beginning of the class and the door question, whatever is inside the parentheses is what you plug in. So inside this parentheses is an x squared. We're going to plug that into g. So I'm going to have square root of this x squared. Now I've already asked you this question today. Square root and square, what happens? They cancel out. So what am I left with? X. That is a linear function. It has no domain restriction. But what was the inside function this time? Was it f or was it g? It was f. So we don't care about g almost at all. I'm going to use this domain restriction, which is no restriction at all. So this one has a domain from negative infinity to infinity. And here's why I'm making such a big deal about it. If you just look at these two questions, we got the same answer for each function, yes? But the order in which I composed them changed, so my domain changed, because it's the inside function that matters, and then the final function. Inside and final. Here's what a multiple choice question might look like for this topic. It says the functions f and g are given by f of x equal to 1 over x plus 1, and g of x is equal to 3x. What is the domain of the function h given by h being equal to f of g of x? Okay, there's a lot of things we need to think about in this question. First of all, what's the inside function? G. Okay, let's highlight with this color scheme where G will be blue, so here's blue. And then the F on the outside will be pink. Okay, that way I keep it all straight. I also know it's going to ask me about the domain of a composed function, so I need to think about the original domain restrictions. For these two functions, what number am I not allowed to plug into F? What number? There's a number I'm not allowed to plug into F. What is it? There's one specific number I'm not allowed to use. If I plug in 0, that would be 0 plus 1 on the bottom, and so it would be 1 over 1. That's okay. Nothing's broken.
Oh, wait. 1 over.
What are you not allowed to divide by?
0.
What number would make that denominator 0? Negative 1. Because if I plug a negative 1 in there, negative 1 plus 1 is 0, and then 1 over 0 is undefined. So I'm not allowed to use negative 1, but literally everything else is fine. What is the domain restriction for g of x? There is none, because what kind of function is it? Nice. So this one has a domain of all real numbers. Cool. We've set ourselves up for success. We understand the type of functions we have, rational and linear. Let's do our composition. You guys told me what was on the inside, but I already forgot. What should go on the inside? G. So I'm writing f of g of x, which means inside of the f function, I need to put the g function. Boom. If we put that 3 of x function in there, into the f function, that means anywhere there was an an x inside of f, you're going to put 3x. So here where the x went, I'm putting 3x. 1 over 3x plus 1. Okay, question. To answer the domain, I need to find the domain of the inside function and the final function. One more again, which one did we put inside?
G of x.
G of x. So we want this one. We don't really care about f's domain right now because it was not the inside function. Then we go look at our final function. Similar to f, what number am I not allowed to plug into the bottom?
-1.
If I put -1 there, this would be 3 times -1 plus 1. That one's okay because that's -2 plus 1, which is -1. What number? It is a fraction. Am I not allowed to use? Close, super close. negative 1/3. So x is not allowed to be equal to negative 1/3 here because 3 times negative 1/3 is negative 1, and negative 1 plus 1 would be 0. If you're sitting here thinking, how did you get that problem? Technically, this is what we did. Subtract 1 from both sides, divide by 3. So if we look at our answer choices here, you'll notice that I have a typo. There's no correct answer. So here's what we're going to do. You're going to mark this part out right here. You're going to make D the correct answer. Inside function, final function. Let's leave the concepts of domain alone for a second, because a lot of the main skills I need you to be able to do is actually composing these two functions and evaluating composed functions, which is what's going to mainly happen on the back. In example 5, it says the functions f and g are given by the functions that you see there, x plus 2 and x squared plus 5. Which of the following is an expression for g of f of x? First things first, which function is on the inside? Nice, but we're going to keep our same color scheme, so f is going to be still pink for me, and g is still going to be blue for consistency. And we're just going to have to compose these two functions. Okay, if I go to do that, I'm going to use a bit sturdier of my color scheme here. If I'm putting g on the outside, and I'm putting f on the inside. Agreed, but let's start from the inside out. So what should I put inside the blue parentheses?
X plus 2.
Nice. All right, so I have g of, and then f of x is x plus 2. Now here's where it gets interesting because this hasn't happened before. If we go to plug in x plus 2 into that outside blue function, how many x's are in that outside blue function?
None.
In the blue function?
Oh.
There's 2 x's, which means you're needing to replace both of those x's with the pink stuff. So it would look something like this. We'd have x squared, but that x is actually x plus 2. Plus 5 times x, but that x is actually x plus 2. I'm taking the blue function, and wherever the x was, I'm substituting in x plus 2. Now, if this was an answer choice, we'd be done. But if you notice, our answer choices are all in standard form, which here comes our algebra for a moment. My question for you is, what is this telling you to do? Square it. So that means, how do we square it, though? Yes. We would call it maybe something that starts with an F. Ooh, I like that one. That's a good one. Factoring is a good one. So it starts with an F. Maybe if I wrote it like this, it would come to mind because we have x plus 2 written twice.
It's not factoring.
No, it's already factored technically. How about FOIL?
What's that?
Thank you for asking. FOIL is a method of distribution where you're multiplying the first terms, the outside terms, the inside terms, and the last terms. This is distributing, but a lot of people teach this to you called FOIL, and that's probably what I'm going to say a lot. You're going to FOIL this guy. This becomes x squared plus 2x plus 2x plus 4. And then what's going to happen with this 5? That one's distributing, single distribution. This becomes plus 5x plus 10. We combine all of our like terms. We only have one term that's squared, so it's just x squared, but we have 2x and 2x and 5x. That's 9x. And we have 4 and we have 10, 14. So not only did we have to know how to do composition, that's the blue and the pink stuff, I then had an algebra question afterwards of simplifying. Okay. Once we've done some composition with functions themselves, We are also going to be asking you to evaluate composite functions. Now your warm-up today, the blue kit, was me asking you to evaluate regular functions. So this is just doing it multiple times to evaluate composite functions. So when this happens, we are going to work starting on the inside. Starting on the inside. What will happen is we will look at what's on the inside of the function, which is g of some number. And we're going to actually figure out what g of some number is. So maybe it says g of 5. And you're like, all right, g of 5 is 8. That output that we found, the random 8, is now going to be plugged into the outside function, and we evaluate one more time. For example, if we start off right away, let's again keep our color scheme of f and g. The first question asks me to do f of g of 3. If we start on the inside here, to do f of g of 3, it's asking me to do f of, I like to write these problems like over again, so I have my color scheme on here, f of g of 3. G of 3 is where I start. We're going to take the number 3 and plug it into the g function. So here's what it might look like. We'll leave the f there for a second. This is 2 times 3 plus 1, because I'm taking 3 and plugging it into the g function. What is 2 times 3 plus 1? 2 times 3 plus 1. 7. So this becomes f of 7, because 2 times 3 plus 1 is 7. Well, now f of 7 is telling me to take the output I got, 7, and immediately plug it back in, but to a different function. So f of 7 is asking me to do 3 times 7 minus 5. What is 3 times 7 minus 5?
3 times 7 is 21.
And then 21 minus 5? Boom. Shall we see another before I make you try one? Okay. Part B, how would you say that out loud? G of f of 3. Nice. So what's the inside function this time? F. All right. We've got that clear. Let's go ahead and do it. So we're doing g of f of 3. Same number, but composed differently. This time, the inside tells me to plug 3 into the f function. So here I go. We're going to do 3 times 3 minus 5. Well, what is 3 times 3 minus 5? 9 minus 5, which is 4. So I have g of 4. G of 4 is telling me to plug what number into g? What? We're plugging in what number again? 4. Whatever number's in there. Whatever number's in the parentheses, right inside of a letter's parentheses, you plug her in. And what's 2 plus 4 times, or what? 2 to, what? Oh, words are hard. 2 times 4 plus 1. Nice. All right, so boom. We get it? You guys are going to have letter C. But before I let you completely, before I completely go, how would you say that one? Correct. F of 4. Follow the instructions. What's on the inside? What's on the outside? Give it a shot. Let's see what happens first. If you're stuck, here's what your first step might look like. We're taking 4 and we're plugging it into F, because that's what's on the inside. What is 3 times 4 minus 5? 7. So my next step would say F of 7. Now I'm not switching functions that I'm plugging it into because it still says F, but now what number am I plugging into F? 7. So this would look like 3 times 7 minus 5. And what is 3 times 7 minus 5?
16.
Nice. Okay, do we kind of get the gist here? Yeah. What if I increase the number of functions that you're having to use? Meaning, for the next 4 in example 7, you don't have just f and g. we have K and H and P and M. I'm not color coding this one because it's too many colors. But you are going to have to choose which of those 4 functions you're using because you're not using all of them every time. Can I let you play? We need to see one? Okay, I'll give you one, but then you have to do the other ones. If we're doing K of H of 2.
Oh, like the big
No, do the harder one.
Do the middle one? Nah.
Okay, Mr. Dog.
We want to do the first one at least then.
What if, okay, you're panicking because of the little circle, right? If you say it out loud, how would you say that?
H of M.
So if I write it the other way, it would be H of M of -1. Both are appropriate ways to write it. Is that what we were stressed about?
Are you just using different formulas for each question?
What do you mean by formula?
Like,
You just plug in and plug
like for this one, we have to use
We have to use these. These are the 2 main functions we have.
for these.
We have these 4 functions. But doing the same thing, you're plugging a number into something to get a number out. You just happen to have more options this time. If I was doing A, I'm gonna talk. Well, I'm gonna do it without talking. So if you're still working, you don't have to listen. But if you're stuck, you can watch.
Wait, could it be negative? It can't be negative, right?
It can, because you're just evaluating a function.
Oh.
Wait, so Ricky,
Oh, I'm gonna say this been wrong. I thought this been wrong.
Okay, again, if you're stuck, I'm gonna start to put my work on the board, but I'm not gonna say anything because I think some people are still thinking without me. I'll do both B and C. Thank you.
whenever you're doing a square root, would you want to solve
Oh, I did.
You got it? Nice. What's your question?
would you want to solve the equation then do the square root, or do you want to do the square root over everything?
You want to simplify the insides before you take the square root. And again, I'm going to work this one quietly so that if you're still working, you can.
Yeah, I definitely looked a little the inside is square root of 3 times 5. So when you do the square root of 3, you see times 5 plus 1. You do 16, the square root of 16 is 4, I think.
Mm-hmm.
Like I just don't know how to write it on paper. So 16 plus 5 is 32 plus 5 is 37. Yeah, I can't do it on paper. Like I get it in my head.
What keeps you from doing it on paper?
I don't get how to write it. Like in my head, I can do it in my head.
If you separated them and you said P of 5 equals 4, K of 4 equals 37, does that make sense?
Like I see like as you started it, after that I knew what to do.
Corey, so do the first one you do is the inside, and then the second one you do is the one that's outside.
Like
That's how
after
I
you
put it.
did the 3 times 5 plus 1, after that I knew what to do. It just when it comes to writing it down, I kind of get lost.
So one suggestion I can have if you're getting lost here is you can separate them, meaning I can be like, okay, well the inside is P of 5, and I'm just going to do P of 5 like this. And I know that's going to be 4. And then I'm going to go back and I'm going to do K of 4. So that if it's all the inside and outside part is what's confusing you, you can separate them like that as long as the output becomes the input. That's what this notation is saying.